So we just finished talking about how to assign oxidation numbers. So now let's look at how we can utilize that type of knowledge to assess a reaction. So in order to identify if a redox reaction is occurring, we have to assign oxidation states to atoms. And that means both the reactants and the products. And so if we look here, we have carbon and it's present as a solid. It's not bound to anything. It doesn't have a charge on it, so we're left to assume this is in its elemental state. So it has an oxidation state of 0. Same with this sulfur, although we've simplified it down because technically the elemental form of sulfur is S8, but we'll avoid getting too in the weeds about that for now. So this also starts at an oxidation state of 0. When we go over to this side, we actually have a case where we have carbon and sulfur where we don't have any rule to determine what the oxidation states are here. And so we're going to have to loosely follow the rule that oxygen follows. So we know that oxygen has that typical charge of -2. Sulfur's in the same column. And so we're going to extend the same courtesy to sulfur and say it has an oxidation state of -2. If we go ahead and do our normal check to see what carbon's oxidation state is, we know that we have a single carbon with an unknown oxidation state. You have 2 sulfurs with an oxidation state of -2, has to be equal to 0. So we have x minus 4 equals 0, and x is going to be equal to a plus 4. So we look at this, and we're just going to now compare each of our different species here. So we're going to look at what has happened to carbon and what has happened to sulfur. And if we look at this, carbon went from 0 to +4. And if it has become more positive, what we're going to say then is that carbon has probably lost electrons. And if it has lost electrons, that means it has been oxidation is lost, has been oxidized. Sulfur, on the flip side, has gone from 0 to -2. It has become more negative, and that's a reduction in charge, meaning that it has gained electrons. And we would say reduction is gain, so it is reduced. Because here we went from 0 to +4, and here we went from 0 to -2. Okay? And if we assign what type of agent each one of these is, carbon is the agent that gave up electrons, so it allows reduction to occur. It is the reducing agent. And the key thing here is that whatever act that has happened to it, oxidation or reduction, the agency is the flip side. And then sulfur is that which allows oxidation to occur because it itself is reduced, so it's the oxidizing agent. Okay. And we can do the same thing. That was our two nonmetals together. We could do the same thing with metals. And so we're going to look at this reaction below. I'm just picking some nice colors for it. And here we see that zinc starts at 0. Iron starts at +2. Zinc then goes to +2. And iron now goes into an elemental state of 0. We draw little lines. Zinc goes from 0 to +2, so we can conclude that it has been oxidized. And then iron goes from +2 to 0. It has become more negative, so it is then reduced. Okay? And so let's go ahead and practice this with a slightly more complicated example. So here we have a reaction, and we're just going to go ahead and assign oxidation states. And we'll do some more practice in lecture on Tuesday, but we look at magnesium. It's a solid, uncharged. We'll conclude it's in its elemental state. Now we come over to water, and water will have a very predictable set of oxidation states that follows the rules we have talked about before. Oxygen, -2, hydrogen, +1. Okay, now we'll go over. We have magnesium hydroxide, which has a lot going on. So we're going to go over to hydrogen here first. It's in its elemental form, so we'll say it's 0. We'll go back over here for hydroxide. We're going to see that the oxygen and the hydrogen follow their usual rules of +1 minus 2. And if you wanted to prove this to yourself, you know that OH minus has a negative charge. If you have an oxidation state of -2 here, 1 of +1 here, that does sum up to the charge there. All right. So now we have to look at magnesium. And so we're going to treat the OH now as a unit, although we don't have to. But we're going to say that magnesium has an unknown oxidation state. And then I'll approach this two different ways. We'll approach it with each atom separately. You have 2 oxygens with an oxidation state of -2, and you have 2 hydrogens with an oxidation state of +1. Okay? And so this is treating each atom separately. So you'd have X -4 plus 2, and all in all, this has to equal 0 because that's an uncharged magnesium hydroxide. So then you can bring the -4 and the +2 to the other side. Before we do that, we can sum them together. You get X minus 2 equals 0. So we get that X is +2. So we can assign that here. We can say +2. And if you wanted to do this the other way I was mentioning, you could say magnesium has an unknown oxidation state, and you have 2 hydroxides that have that sum of -1. I'd say it's probably better just to do this full atom accounting, but you can always check to make sure that, hydroxide itself is bringing that -1 charge. And so because it is a charged molecule, the whole thing has a summed oxidation state of -1. And so what we can do now that we've assigned all these oxidation states, and I find it easiest to do this, is we make a table. We put reactants and products, and we're not going to write, the actual identities of our reactants and products. We're just going to write each of the atoms we're looking at: magnesium, hydrogen, and oxygen. And we're going to see what their oxidation states are before and after. So we said magnesium starts at 0 and goes to +2. Hydrogen starts at +1, and in one case is +1 with the OH, and it's also 0 with the H2 gas. Oxygen starts as -2 and ends at -2. And we're making sure to put any entry in. So however many blues we see, we put whatever oxidation state each one of those things are. So we see that our species that have changed are going to be magnesium, and they're going to be hydrogen. And we see magnesium, it's going from 0 to +2. And what we're going to conclude here is that it has lost electrons, so it is oxidized. And then on our second here, we have hydrogen, which went from +1 and focusing on its change has gone to 0, meaning that it has gained an electron, and this is what has been reduced. And so we're going to continue to practice with this on Tuesday, but this should give you a general idea of how we approach these types of reactions and how we'll look at them moving forward.